sorry I'm starting a little late, so let's get moving. So last class I talked a bit about sort of a Wittig-elimination, and I left you guys off with the general mechanism, right, of where if you want to sort of take a carbonyl of some type, specifically aldehydes and ketones, we'll see later on, this doesn't work with esters, but if you take them and you treat them with R1, if we treat it with, make sure this is running. Oh, first of all, so this happens every once in a while, and I apologize, but it's sort of one of the reasons why I make the announcement early on. I can't guarantee that these videos will all be online. Last Wednesday was a perfect example. I went up to my office, I went to put it online, and suddenly the video was gone. And I don't know where it went, even though I thought I recorded it. So I don't know sometimes what happens. So I unfortunately don't have last Wednesday's video. But I will try my best, and I'll, like I did, I put up an alternative video that should at least supplement those. Okay, so anyway, so last class we talked about the Wittig-elimination, and we went through the generic mechanism of the reaction, and what we sort of mentioned is that you're making alkenes, and these alkenes, the fact is that if you're generating these alkenes, you can imagine there's a stereochemical outcome that can actually take place through this process. You can either get the sort of the E alkene, right, or you can get the Z alkene. Now I'm going to show you guys a little bit about sort of some of the thought processes behind how people rationalize formation of one versus formation of the other. But before I get into that, of the two molecules, right, the E or the Z alkene, in general, which one of the two would you guys expect would be thermodynamically favored, more stable? Yeah. Right, so the trans, right, would generally be more stable. So we would expect this to be more stable. And I'll come back to that later on. So I'll just sort of say where we're going to be going with this in terms of the big picture, right, is this will sort of represent kind of an idea of kinetic versus thermodynamic control, right, where when you run a reaction, right, if it's reversible, right, the reaction can end up going to the more stable, thermodynamically stable product. Whereas if it's irreversible, if it just so happens that of the two pathways, one happens to go to the higher energy overall product, but that pathway happens to be lower in energy than the pathway to the lower in energy overall product, then sometimes you'll get the higher energy. So that's sort of kinetic control. And so overall, what we're going to see here is that when these Freudian slip, when these Wittig-ilids are stable, less stable. Right? Basically what's going to happen is if you have a less stable Wittig-ilid or an unstable Wittig-ilid, what we're going to see is that we get to the less stable product, or the lower in energy. I mean, less stable is a bad word, lower energy. Higher energy. And this will be the sort of the more stable Wittig-ilid. And we'll sort of, it'll make sense once we get there. Okay? And so, in general, most Wittig-ilids that we use, they're going to be based, as we said sort of last class, right? They're going to be based upon taking some type of an alkyl halide, right, and treating the triphenylphosphine followed by base, as we sort of stated last class, right? So, but if that R group, perhaps I'll show you the stabilized one first, because then it's a little bit easier to see. Here's an example of a Wittig-ilid where you actually have sort of the negative charge, sort of alpha to this ester there. What's going to be the impact of having that negative charge alpha to the carbonyl? Right? Is that going to make it more stable or less stable? More stable, right? Because of resonance. And this will reinforce what we're going to talk about shortly, which is enolate chemistry, right? But you can actually stabilize that negative charge right, through resonance. And so in general, I should say more stable Wittig-Illid. So in general, when we start talking about more stable Wittig-Illids, what we're generally talking about is systems where you can have resonance stabilization, right, of that sort of anion there. So that resonance form will help stabilize it. So as we'll see, and then I'll go through some of the sort of thoughts behind why this is the case, if you have that stabilization, you're going to get to the lower in energy product, so the thermodynamic product, if you will. If you don't have that stabilization, right, that's when we'll sort of call it an unstabilized Wittig-Illid, or less stable Wittig-Illid, and it will go to the sort of the Z double bond, right, the sort of the higher energy one. Okay, so that's sort of the bare bones behind this. More stable Illid, more stable product. Less stable Illid, less stable product, and I'll explain some of the.
Can you give an example of less stable?
Just get rid of the carbonyl, right? So if you just get rid of this, right, and that's a CH3, right, you no longer have that resonance stabilization. So when we're talking about stabilized Wittig-Illids, in say this class, what we're going to be referring to exclusively is Illids where the negative charge can be stabilized through resonance. If the negative charge cannot be stabilized through resonance, then we're not going to have it. Now the book talks about an alternative Wittig that's called the Horner-Wadsworth-Emmons reagent. I don't cover that generally. It's the exact same thing as the Wittig in terms of what we're learning. There are some advantages to Horner-Wadsworth-Emmons oleifinations in terms of technical advantages. Specifically, they're a little bit cheaper to make for that specific class of reactions, and they're sometimes easier to wash away and stuff. But I think for the sake of this course, we'll just focus exclusively on Wittig. Okay, so triphenylphosphine-based sources, yeah.
Will you get two on one will just be the main product, or you will only get?
It depends. An example where you get a mixture, for example, is bromides, halogens. If you have a bromide there, but that's a little bit more advanced. I'm not gonna, but like, so you certainly can get mixtures, and this is one that's well known to get mixtures because it's a little bit stabilized, but not so much, and so you get that sort of mixture. Okay. All right. So okay. So why is this the case? I thought, you know, I've gone through this in various capacities in the past in terms of explaining this, and I think I'm going to give it a shot again this year, in large part to try to reinforce something that you guys may have not seen in a while. Right, we're going to see some chair confirmations. I want to talk a little bit about Newmans, and I think Newman projections and revisiting Newmans is certainly something that's going to be beneficial. And so I'll try to sort of explain to you the theory that has somewhat been disproven, but it was largely the sort of the working theory for this process for up until maybe about 10 years ago. But I'll show it to you anyways because I think it serves as a good sort of idea of how people use structure and ideas to sort of explain some differences in reactivity, okay? All right, so when you have a carbonyl, right, you have sort of a proton, right, and you have an R group, right? And we're going to sort of attack this with a Wittig-Illid, right? But our Wittig-Illid will also have a certain degree of you know, it's not just an R group, right? You also have the proton that you have to consider as well. And so the theory used to effectively be that what would happen, right, is that when the group approached, so this is R2, this is R1, this is R2, this is a proton, right, that basically when this Illid attacked that carbonyl, the transition state barrier to that sort of resembled somewhat of a Newman projection, okay? And what you'll see is when I draw the Newman projection, right, we have a couple options, right? I can draw them with the R2 on the same side as the R1, or I can draw them sorry, I could draw them on the opposite side, or I could draw them on the same side. So let me sort of draw those sort of Newmans. Okay, so I'll start with the lower energy Newman. Okay, and what I will do is carbonyl in the back, right there. Positive, negative charge. All right, so the R2 is over here, and the H is over there. Now there's questions about, well, why do I put it like this? Well, this is part of the theory, and I'm not going to go too much into depth, but ultimately the sort of the transition state behind why they believe that the Wittig olefination led to sort of Z double bonds with unstabilized is sort of going to be explained through this sort of theory. So you guys kind of see how this, I just put stack one on top of the other, but I've sort of drawn it in a way that resembles, right, a Newman rejection, right? And so if you can imagine that that reaction is going to take place, right, that's going to add in, we're going to end up with the alkoxide. Now I've got the O there. And what we've done in this, right, is we've kept the R1 and the R2 away from one another. I could have drawn it the other way, but in that case, the R1 and the R2 would have been having, what's that interaction called? The Gauche interaction, good, right? Okay, so now I've sort of drawn it in the sort of form that we need. Now, if you remember last week, I'll re-quiz you guys, what needs to happen in the sort of last step of the Wittig olefination? Do you remember? Yeah, what is it? Of what? What kind of formation of a... Yeah, it's like a cyclic ring structure. So which bond do I want to form? Oxygen and phosphorus need to make a bond. So basically, looking at this Newman projection, which sometimes is just easier, this is an example where perhaps it's a little bit easier to see in the Newman projection, what we're going to do is we're going to rotate that phosphine up so that now it's, in essence, right, to make that three-membered ring, the phosphine now has to be eclipsing the oxygen. So let's go ahead and do that. So I'll rotate that phosphine, so I'll just draw the back first. And watch what's going to happen. Just horrible. Right, what's going to happen is if I rotate this 180 degrees up, the R2 is now going to be eclipsing with the R1. Protons are going to be eclipsing, such that when it sort of makes that bond, right, and does the elimination, I guess, that we did before, the R2 and the R1 are on the same side, and so the product, right, upon elimination becomes the sort of Z double bond. Does that make sense? Right? So the argument, yeah.
What happens to the charge in the center?
So basically this had the charge here, I added it in, and so I have the alkoxide.
So I thought you got the double bond.
What are you talking about? Here?
No, the other.
This one.
Yeah.
So I had an anion here, so there's no bond being formed here. This is basically, I just took this and moved it up and made it into a Newman. So I hadn't made the bond yet. So this was just lining them up, right, to sort of see how this ylid and this ylid could line up, right? Then I basically just had this, in essence, attack carbonyl. Right, does that make sense? It's tough to draw. You can't really attack the carbon on the Newman because the Newman's kind of hidden, so which is why I sort of left it. But you understand what's going on, right? The anion is attacking the carbonyl. I was just trying to line them up. So yeah. So what happens, right, is over here you generate, you can draw it in different ways. You can draw it like this. You can draw it, usually people draw it like this. Right, it's the same molecule. Just sometimes people will draw it as a double bond, sometimes people will draw it as charged. Okay? But yeah, that's going to sort of leave. Maybe I should have drawn the electrons the other way. But the point is that you're sort of eliminating in this sort of conformation. So the initial bond forming event, right, which is basically between here and here, right, is the bond forming event where the R2 and the R1 are anti to one another, right? And what happens, right, is because this ylid is not stabilized, right, this is now not reversible, right? So once it gets here, it can't go anywhere else. It has to go this way. So the energy barrier to reverse is too high. Does that make sense? So the non-stabilized ylid, once it makes that carbon-carbon bond, it can't go back, right? So it has to proceed to the product, and proceeding to that product requires, in essence, going to that sort of eclipsed R1, R2 double bond, okay? Now, if this was a stabilized ylid, right, now this becomes reversible, right? Does that make sense? So if the ylid, if suddenly this is more stable, this can go back, right? And because this can go back, over time, right, it can flip and go the other way, which is locally higher in energy, but what that does is, again, based on rotation, right, what will happen is, over time, you will get this attack. Right? So again, it's a mixture between these two, right? If you allow this to be reversible, eventually you'll get some to go through this pathway, which ends up being lower in energy, not necessarily at the beginning step, but it basically ends up being reversible. It ends up being lower in energy at this next step, right? Because in order for this one to eliminate, right, you need to have an eclipsing R1 and R2. So in the case of the stabilized ylid, because of the fact that it's reversible, it will eventually want to go through a later downfield step that's lower in energy, which ends up being oops, 2 H R1, right? So now, in this case, we have eclipsing versus the R1 and the R2. But because it was irreversible, it has no choice but to charge forward. You see that? On this one, this is lower in energy than this. And because it's reversible, it can proceed through this pathway, which will ultimately lead, now you've got the R1 and the R2 on the opposite sides, and once that eliminates, eventually gets to the trans. Does this make sense? Right? So it's a little bit complex. I decided to, sometimes I go through this, sometimes I decide not to. But I thought we had time, and I thought that we could do it. It helps reinforce how, for example, that Newman projection, which we learned last semester, it sort of helps reinforce how people sometimes use these to sort of see how this process takes place. It also sort of helps explain how people start to think about how a reaction, right? I think it's a nice example of how a reaction can actually lead to the less stable product, right? So I think it's a nice example of that because we don't see that all that much. So here's an example where this sort of the first step, reversible versus irreversible on that first step is going to dictate which way it goes, right? And if it's not reversible in that first step, then it has no choice than to charge forward and go to what is ultimately the lower in energy product. So, okay? So yeah.
Isn't a stable video, like, doesn't it start off with the oxygen having negative charge?
You could draw it as that. I mean, that's just an enolate.
Oh.
Yeah, that's just a resonance form. It's all resonance forms of one another. We'll talk a little bit about enolates, and I don't know if where you're heading is the oxygen being the nucleophile versus the carbon. That's something we'll get into a little bit with enolate chemistry. But in sort of undergraduate first, second semester organic chemistry, we rarely talk about oxygen being the nucleophilic source within those enolates, and it's something we don't get into that much, but it's a molecular orbital versus sort of charged interaction argument. Yeah.
So that one, is there a positive charge on page 3?
Yeah. Yes.
If you were to ask, like, how to draw the mechanism from that to specifically the cis or specifically the trans, would we have to use like the Newman?
I could see myself asking on an exam, for example, the next exam or the final. I'm not saying I'm going to, but certainly I think it would be fair game to say, hey, explain why this non-stabilized ylid leads to the cis double bond.
And then like we would use Newman.
You could use Newman. You could try to use a sawhorse or something like that as well, but I think the Newman is easier.
Okay.
Right? So, if you were having to explain it, you want to explain things with structures, and the Newmans, I think, would be the easiest way. But you could potentially try to explain it using structures in some other ways. But again, I think the Newman just simplifies sometimes seeing these. And so this is one of the reasons why I decided to talk about this. Okay? So I hope this wasn't overly confusing. But I do think that it's a bit of a nice representative example, as I said before. I don't want to restate myself again. Yeah?
Would you want like a picture like that, or could we just say something like because it's
I would want structures.
reversible?
Yeah. Structures. Exactly. On. As I stated on the first day of class, this is as much an art class as it is a science class. Drawing the structures, we communicate through the structures, and so the structures say 1,000 words, and so absolutely I would want to see the structures. Otherwise, your words wouldn't really help. Yeah.
On the structures, just
Sure, go ahead.
So to find that it's non-reversible, can you just show where it looks like it's non-reversible, and that's how we know?
So the reversibility is going to be this step here. This is the key reversible step.
Yeah.
Right? So those two, the addition of the ylid versus the reversible nature of that ylid. So basically having the ylid react and then reverting back to the ylid. That's where the stabilization of that ylid comes into play. So if it's a stabilized ylid, it will be reversible. If it's a non-stabilized ylid, it will not be reversible.
And we know that it's not reversible because it ends up being the way it's eclipsed. The RNA, like it ends up being cis when
So, well, whether you know that the ylid is reversible or not is based upon what I was saying earlier, the stabilization of those ylids through resonance. And so, again, there's other ways that you might imagine it. For example, I showed how the halogen can give you a little bit, but that's also sterically a bromide versus a proton is not that big. So there's steric considerations for why a halogen would, for example, give a mixture of E and Z. But for the most part, what you're going to see in this class is you're going to see resonance stabilized substituents and non-resonance stabilized substituents. If the resonance stabilized substituent is on there, and again, you have to make sure that it's actually in conjugation, right? So it can't be multiple carbons away. It has to be where there's the resonance stabilization. If that ylid anion can be resonance stabilized, that's going to render it reversible, and that's going to lead to the lower energy process. So where could this come up, right? In terms of thinking about exams, quizzes, and stuff like that. Well, if I ask you for a product, right, and I give you a Wittig reagent, right, you're going to have to identify, right, especially if there is E or Z, double bond geometry that can be formed, you're going to have to identify, is that Wittig ylid stabilized? Is it non-stabilized? And again, that's going to be about looking on whether that would have resonance, right? And then you would have to tell me, if it's an E or Z double bond, right? And then I could also ask a question like this. Yes?
I'm just a little confused because in the beginning, you started off as like the less stable one automatically, the more stable one, started off.
The more stable product or the more stable what? The more stable one being what?
The more stable,
Intermediate? Local intermediate?
yeah. So you started off with two different, like over there you already started off with both R's on one side.
Right.
And
So
that's why
so let me try to just say it maybe in, not maybe simpler, but let me just sort of get to the point, right? This, to this has the R groups anti to one another.
Right.
This is lower in energy than this, right? But this, which comes from the lower in energy one, is higher in energy than this, right? So once you get here, basically, if you can get up that energy barrier, right, like that's a higher energy barrier because it's eclipsing, right? So thus, if the whole process is reversible, you know, because this is a higher energy eclipsing process, it will funnel itself through this pathway.
Okay.
If it's non-reversible, then it's not going to have that option.
Okay.
Does that make sense? Okay. All right. Yeah.
I mean, I could ask it later, but
That's
is
fine.
one endodermic, one exodermic, or
Exothermic, endothermic.
Yeah.
Vitigulfinations are, I believe, both exothermic. I think.
so I'm trying to
Yeah,
think of
most
like
of the reactions that, I think endothermic, exothermic reactions, I mean, overall, it's driven, triphenylphosphine oxide is a driving factor in this process. So. Okay,
Professor,
yes.
if that is the more stable one, why does it go there, then go back into there?
It never is able to get here. Wait, sorry,
The more,
restate
more
what you
stable one.
The
So
more
the
stable
stable
illid?
one, yeah, goes through that, and then it can reverse back.
It never, so because, okay, this, right, is lower in energy, right, than this.
Okay.
So it's easier for it to go here and then pass through here than go over this energy barrier. Okay? All right. One last question, then we get to Abraham.
If you run this reaction in class, what percentage of your product will be the higher stable? What percentage?
So, for your guys' sake, right, that's the question that came up earlier. Do you get mixtures? And I gave an example. It's going to be very substrate specific whether you got a mixture. I gave halogens as an example, right? If that R2 was a bromide, you get practically a 50-50 mixture, right? You don't need to know that. I'm just using that as a representative example. For your guys' case, again, if you get resonance stabilization, go to trans. If you don't have that resonance stabilization, go to cis. And if you're ambitious, this may come up on the exam as well, understanding it. So, okay? All right, let's move on. All right, so that's the Vitig-olefenation. Certainly it's a little bit more complex. Okay? All right, so there's going to be a few other... So today there's going to be a few challenging... There's going to be another challenging mechanistic question that we're going to go over today. So before I get to that one, I will show you one that you don't need to know the mechanism for. Simply to sort of, because I know that can be challenging. So we talked yesterday, or last class, we talked about how alkene reductions are adding hydrogen across double bonds. And carbonyl reductions are also like adding hydrogen across double bonds. And what we sort of showed last time, right, was specifically sort of the classical way that people reduce aldehydes and ketones. Do you guys remember what that reagent was? No, that's oxidation. If we want to reduce a double bond to an alcohol. Yeah, so it's usually sodium borohydride, lithium aluminum hydride, which we'll talk about, which is a little bit more important for esters, as we'll get to. But yeah, so that's the situation. Again, we're adding hydrogen across it, but we're kind of adding H minus, right, into it, then sort of quenching it with H plus. So formally, that's a situation where we're formally adding hydrogen gas across it, but it's in the form of H minus followed by protonating, so H plus. So, right, that makes sense. But when we talk about alkene chemistry, right, within alkenes, we learned how to reduce alkenes, and we actually physically used hydrogen gas, right? And so the use of hydrogen gas in reductions is common, and we've seen that in the past. And so it's perhaps not surprising, right, that there are certain types. You can certainly also use hydrogen gas with certain metals. What do they usually show? Like platinum oxide is, I think. So if you use like platinum and hydrogen gas, you can actually reduce the alcohol. And if you have a system, but platinum and hydrogen gas can actually also reduce double bonds, right? So worth noting, if you have platinum and hydrogen gas, you actually get the same thing, right? Because you add hydrogen across this and hydrogen across this. So a lot of sort of metal-based reductions, I'll just sort of point out that a lot of metal-based reductions are, it's generally, when people are doing hydrogenation with double bonds, carbonyls, it's usually, how do I put this? Basically, the metal-based hydrogenation conditions to reduce carbonyls are oftentimes not all that selective. Okay, it's a little bit easier to reduce a double bond in the presence of a carbonyl. So what you could do, and again, this is all baloney to a certain extent. It's more complicated than this, but they give you a few metals just so that you can sort of practice that sort of orthogonality, and so just keep this in mind. Rhodium catalysts. And there's truth in it. It's not complete baloney, but I'm saying it's just more complicated than, you don't just use rhodium. It's usually rhodium catalyst of some type, right? But the book tried to keep it simplified, so I will too. Right, that you could selectively reduce a double bond, right, in this case, right, in the presence of the carbonyl, and you can get to a species like this, right? If you wanted to selectively reduce this, what's that?
Protected?
Are you?
No. If you wanted to selectively reduce this, if you wanted to get to something like this, right? If you wanted to get to something like this, what would you do? You use like the borohydride reduction or something like that, right? So you use the borohydride reduction. It's a little more complicated than that. You usually need like certain Lewis acids and stuff because you can certainly get competitive, especially in situations like this. As we'll sort of see, this is a conjugated system, so you can get competitive addition here. But, let's just say sodium borohydride is what you use. So I think the point that I'm trying to get at here is that we've learned about reductions. What we didn't discuss yet that I wanted to make sure that we addressed is that we've already seen reductions on double bonds. When you're doing reduction chemistry, it's not always selective for one over the other. Sometimes certain metals will do both, right? But there is the possibility, and chemistry has been worked out to give you selective, which we've already kind of seen, so you can certainly do this reduction. And if you use like a softer metal like rhodium, I don't know if that's the right term, but if you use rhodium in this case, you can actually get that sort of product as well. Yeah.
I think I read in the book that RU, it's a metal RU.
Ruthenium and rhodium, what's that?
Same thing as NADH4.
They're both platinum.
That ruthenium, in terms of selectivity, it's possible. Again, like I said, it's a lot more complex than just the metal itself. So I'm sure that people have figured out metalloenzyme-based, like metal hydrogen ways to select for this. I'm sure. And usually, what you use, even with sodium borohydride, is you do something called the Lusch reduction, which you use cerium in there as well. So, so I believe it. Okay. All right. All right, so this is going to transition into additional type of reductions. So if we reduce alcohols and carbonyls, can I erase this? Okay, so much like we were talking about oxidation in terms of going to the sort of carbonyl, you can actually reduce this even further. Right? And you can add hydrogen across this as well. Right? And much like in the case where we were talking about the sort of terms of oxidation and reduction within sort of Jones oxidation, you're sort of losing water here. So formally, we're still adding an equivalent of hydrogen to this. Hydrogen is still basically going into the system. This is what's generally referred to colloquially as an exhaustive reduction. And there's a couple ways that you can do this. One of them is, again, more metal-based, called the Clemmensen reduction. And then the other one's a little bit more mechanistically complex, and I thought we would spend some time going through it. It's called the Wolff-Kishner reduction. So if you wanted to go sort of all the way from here to there, Clemmensen is one option. Mercury, what is it? It's a zinc and mercury. HCl. So basically, I think the way this works is I think you end up generating like zinc hydride sources that can sort of add in there. We do some exhaustive reduction chemistry from like halogens with stuff that's somewhat similar, but I think the mercury helps. I'm guessing makes the water a little bit better leaving group in there for this Clemmensen reduction. But mechanistically, this is a transition metal process. The book doesn't discuss the mechanism. I could probably come up with a mechanism, but I don't think it falls in line with much. But the mechanism that's a little bit more challenging that you are going to be responsible for is an alternative method, which is called the Wolff-Kishner reduction. Okay. Okay. And the Wolff-Kishner reduction, the first step of the Wolff-Kishner reduction is going to be analogous to something that we've seen before. So the Wolff-Kishner reduction, once you sort of understand it, it's a lot going on to it. Because as we saw under the acetal forming reactions, right, there's nothing new necessarily about taking a ketone and converting it to an acetal, right? We sort of showed it how everything kind of was in line with things that we had seen in the past, but because there were so many steps, it maybe became a little bit overwhelming. But if you sort of understand it and you understand that there's nothing new within there, it's not quite as intimidating. And the Wolff-Kishner in many ways is the same, right? The Wolff-Kishner is we can break it into a two-step process to keep our lives a little bit easier. And the first step of the Wolff-Kishner involves hydrazine. Okay, and to stay consistent, hydrazine. So hydrazine is one of these really amazingly good nucleophiles. People use it in bioorganic chemistry every once in a while because it's so nucleophilic that you don't necessarily need to activate even the carbonyl, but usually I just throw in acetic acid there just to give us something to work with, right? So at least we're staying consistent. So I'll throw in acetic acid there, but realize that you don't need acetic acid to promote this condensation, but just so that we're not having to separate our charges, I'll throw it in there, right? And what's going to happen here in the first step is you can generate the hydrazone, okay? And so this should look familiar. I told you guys to make sure that you could figure out how amines condense, right? But we'll go through it just to test to make sure that you guys did that, right? And so this is a condensation reaction. We're losing water, so what's going to be the first step? I gave you the acetic acid as a little bit of a gift, right? So however we want to do it, I guess we can do it from here to get to the sort of more, I think, the resonance form that more accurately describes the electrophilicity, right? We could draw the other resonance form here, but this is the one that kind of describes the electrophilicity of the carbonyl, right? It's that positive charge is what's going to take on the electrons from a nucleophile, right? And then, right, should be fairly obvious here what's going to happen next, right? The hydrazine is going to attack, right? So the hydrazine is going to the hydrazine is going to attack. Okay. Okay, so here's I'm gonna give you guys a gift. You guys want a gift? Here's my gift to you. All right. So one of the things that really complicates these reactions, okay, and so bear with me here for a minute, but one of the things that really complicates a lot of this condensation chemistry is that there's a lot of proton transfer events that are taking place, right? So proton exchange from one place to the other, back and forth, okay? And so within these type of mechanisms, you know, how the proton exchange takes place, you know, there's multiple things that can happen, but usually I think just to get through the mechanism, even though this may not be what's necessarily going on, proton transfers are facile. So what I'll do here is I want that to be my leaving group, right? I know that just like in the other mechanism, I want that to be my leaving group. So I'm just gonna, even though it's probably not happening this way, I know, what a gift, right? Sorry, I probably thought I was like gonna give a cheat sheet to the final. But anyway, so what we have here is we basically transferred the proton from one to the other. And again, maybe it's happening intermolecularly, maybe it's not. But that's gonna just, if you do it that way rather than have something deprotonate it, reprotonate it, it's gonna save a lot of lead on your pencil, okay? Okay, because you are gonna see a lot of these events. Okay, all right, so water's gonna leave, okay? And I'm about to run out of board space. Right, H2N, H, right? And this is going to have resonance form with a double bond, and just sort of for bookkeeping purposes, I'll have the acetate come back in, deprotonate it, right? Now I'm going to get to my hydrazone. Okay, does everybody see that? Okay. I'm out of board space to a certain extent, so just take a picture of that, something, because I do have to erase everything. Okay, but basically, it's analogous to what we saw before. Again, the one big difference is we're making a double bond with the nitrogen rather than what we saw in the acetals, which is 2 oxygen double bonds, okay? Okay, so this should be certainly nothing super new, okay? All right, see one more camera up. You set up there? Okay, all right, so that's the first step of the Wolff-Kishner, okay? Oh, I'm going to erase that. Okay, so oftentimes the Wolff-Kishner is actually run with hydrazine as well as base. So the second step generally we think of with base and sodium hydroxide. So you can make the hydrazone, treat it to sodium hydroxide, but truthfully sometimes people will just take the hydrazone and they'll use that as the base altogether. The kicker here, and I think the thing that makes Wolff-Kishner mechanism challenging versus, I think, greatly simplifying this reaction, is if you can notice a tautomer form here. Okay, there's a tautomer, so what we want to do is we don't have any protons here, right? And you can greatly simplify the Wolff-Kishner if you can recognize that you can get one proton there from a tautomer. Okay, remember what tautomers are? If you're being facetious or not. Right? Remember when we were talking about the PCC oxidation and how it was an elimination reaction, but we just had some different atoms around there, right? This is carbon, carbon, oxygen. So it's a double bond connected to, it's effectively in many ways sort of like kind of an allylic-ish type oxygen, right? You've got your double bond and then you've got your oxygen with the proton on it. And then what's happening is you get your double bond there and your hydrogen's up there. Right? Yeah, Rachel. Exactly. So if I make a comparison over there, right? This would kind of be the analogy to, for example, the OH, right? And then we have our double bond here. So what we want to do is we want that proton to be there, right? And we want our double bond to be here, right? And that's you know, we can. Right? We can imagine pushing electrons a little bit like that, where the double bond is kind of dragging that proton. Right? I guess I can draw this too. Right? But it's formally tautomerization. It's kind of like, you know, it's kind of like if you were to draw a tautomer mechanism like that. Right? That makes sense. Right? So the double bond is kind of dragging the proton there, and what we're making here is we're getting one of those two protons. Do you guys see that? Maybe I should just draw it. Let me just draw it so it's maybe a little bit more suggestive of what I showed there. Okay, does everybody see it now? If I draw it that way, it's a little bit easier to see. Right, but basically, the double bond that was here is there, and one of those two hydrogens is now at that carbon. And the analogy that I really want you guys to focus on sort of seeing is how this is a tautomerization. It's analogous to the enol-keto tautomer. So if you're comfortable with the enol-keto tautomer, convince yourself that this is analogous, and you should also be comfortable with this tautomer, okay? Just different atoms in there, but the protons and the double bonds are the same, okay? And this is where, we haven't even brought in the base yet, and just by thinking of that tautomer, we're going to get one of the protons there, okay? But this is where the Wolff-Kishner and the hydrazine is important, and this is where the base comes in. Because if you deprotonate that proton right there with the sodium hydroxide, what we're going to get to is and I think this is the part that ends up being a little bit tricky, but it should make sense if we think about some of the things we've talked about in the past in terms of sort of Le Chatelier's principle and in terms of things that can become gas. We can basically liberate nitrogen gas here. Think about that for a second. What would be a mechanism, now that we have this anionic source, we can effectively eliminate nitrogen gas? And the term we got to be a little bit careful with, because sometimes when you guys think about elimination, you think about the nitrogen taking on the electrons. But in this case, the nitrogen already has the electrons, so it's actually going to go in a different direction, right? How are we going to do this? It's almost like the nitrogen, it's almost like an elimination. It actually is an elimination, you know, almost like the first step if we broke down and deprotonated and then eliminated a bromide, except that your bromide is kind of an alkyl group, right? So Rachel, you had your hand up?
Yeah, I'm not sure where we're going, but the mechanism to keep the hydrogen bond.
Nope. Fatu? So, right, I guess this is sort of, this already has the electrons, so you're not going to be giving it electrons. Yeah?
Would the hydrogen happen the first nitrogen creating the positive charge and then
Okay, so there's another possible mechanism that we can also discuss that's more sigmatropic-y, but let's, yeah.
The electrons from the outer nitrogen make a triple bond with the other nitrogen, and the other electrons go off from that nitrogen to the other nitrogen.
Exactly, and this is probably looks really screwed up to you guys, right? Why would this look kind of screwy to you guys?
They're making a carbanion.
Exactly. Right? So this is going to be uncomfortable, I get, because we've never seen a carbanion as a leaving group. But what else have we rarely seen? The ability to generate nitrogen gas, right? So the fact that you're generating nitrogen gas here, right? Nitrogen isn't staying in the flask, right? The nature, or I should say, it's not going to stay in the solution, right? So that's going to be highly, highly, highly irreversible, right? Because the nitrogen is going to be forming, and the nitrogen is going to escape the system. And then from there, it's pretty straightforward, right? We're just going to protonate it, right? With, I guess maybe we'll choose the water, right, that we showed earlier, right? So we'll have the water, because we generated water there. Right? Okay, let that mechanism sink in for a second. All right, so the hydrazone formation is equivalent. This mechanism is a little bit maybe new feeling, right? But if you can see the tautomerization, then really the one kind of new thing is that sort of nitrogen elimination process. I'll show you another way that we can envision it, but for now, let's see the table. What's that?
In the first part, in the first step.
Yeah, when sodium hydroxide. Okay, so this is, I think, this is the standard way that you guys will probably want to draw it. There is a little bit more. There's a sort of more. How do I put it? Yeah.
I was gonna say, do you have to use sodium hydroxide? Can't you just use the acetate?
Okay, so I'm good. That's where I'm going. So there, well, the acetate. So the.
Which acetate?
Okay, let me just. Sorry, there's a lot of it. Let me just clean this up for a second. The actual process for a Wolff-Kishner is hydrazine and sodium hydroxide. Hydrazine does not require acid to form. It reacts readily, but I think I gave you the acid almost as just a little bit of a way to keep consistent with the formation that we had before. So I was trying to break it into almost a 2-reaction sequence: hydrogen and acid followed by sodium hydroxide. If you want to do it without the acetic acid, that's fine as well. I was just trying to make it be a little bit more consistent. So that second step didn't have the acetate at that point. It was, imagine it like we made the hydrazone with the acid, we isolated the hydrazone, then we resubjected that to sodium hydroxide. That's how I was trying to feed it to you guys. Is that fair?
Yeah.
Okay, yeah.
If we were to add the acid, we have to like specify that it's in 2 separate steps. If you add an acid and a base at the same time, then you can't have like an acid and a base as a block at the same time.
Yeah, I mean you can, so not at the same time, they're going to neutralize each other, right? Usually, but what people will occasionally do when it's a 2-step process is they'll, like, for example, allow the first reaction to take place, right? And then maybe they'll begin to neutralize the process. You probably have to add it really slowly so it doesn't, you know.
Sure, but what I'm saying is like if we were to write it with an acid, should we write step 1?
Yeah, I think it's fine. Or I followed by double I, sort of almost like a one. Yeah, it's fine. Yeah. If those are the questions you have, you're fine. So, okay, so there's another possibility that you can imagine invoking. You know, you could, in principle, if you're really uncomfortable drawing the sort of intermediate, you could invoke a more sigmatropic type process where it's forming at the same time. So something like, you know, do I think that's happening? I don't know. Maybe I should have checked this before I wrote it down. But that would be sort of a more sigmatropic-y type intermediate that you wouldn't necessarily have to do the carbanion. But I think the carbanion is probably the safe way to go. I think it's weird that we're generating this carbanion, but we can reason that based upon the fact that we're generating nitrogen, and the nitrogen is escaping the system. Okay. All right. So I think we're done with at least ketones for now. Okay, let me show you one more reaction because I have it in my notes here.
I have a question.
Yeah.
Before you go on. So that hydrazine, some books show that hydrazine already protonated. What about that? Is rather than
Show
using
already
acetic
protonated?
acid,
Oh, so if like you had this in acetic acid, it would be
like already protonated.
So it would be like- it would be like this.
exactly.
Yeah, that's oftentimes how you like buy hydrazine as well. That's fine as well. Yeah. Okay. All right. So since we're here and since I think it's a logical time to mention this. I wasn't sure if I was going to save this for the amine chapter or not, but I have it in my notebook here, and I think it maybe makes sense to show you guys here. So sort of learn it. So if I were to take, and we'll come back to this in the amine chapter a little bit, but I just sort of want to make a general point here to then introduce an alternative reaction that I think now's the time to discuss this reaction, because we've literally just learned the two things that help bring this together, and it's reductive amination chemistry. If I were to take an amine, this is a reductive amination. So it might be in a later chapter, but I think it's worth discussing now. Okay? So if I were to take this amine, and let's say, for example, that I wanted to treat it with bromoethane, for example, and I was hoping to make this molecule here, I guess I would probably have, right? Let's say, for example, that I wanted to make that. There's a fundamental problem with this reaction that would make it very difficult to do. And that's that, remember that it's not, you're not doing chemistry on one molecule at a time, right? It's a solution. And so you have a whole bunch of this in here, you have a whole bunch of this in there. And so as this begins to form, right, what else can happen? Because you still have this here, you still have this here. This amine base can deprotonate this, right? And what will happen is you'll have some more of the free amine, and then what's going to happen if you've got some of that free amine and everything else can react again. Right? React again. So now you got double addition. You can go through it again. You can get 3 amines. And then you can even get to the quaternary ammonium salt sometimes. And so the reaction between amines and alkyl halides is not a clean reaction. It doesn't work well because there's so many possibilities and so many different things take place. But we learned last class about reductions. We were just talking about amine condensation. So one of the things that people will do to overcome this problem is something called a reductive amination. Okay? And a reductive amination, I'll just sort of use it as an example to make this molecule here, is basically a 2-step process, okay, where the first reaction, you condense it with some acid, okay? And the second step is, I'll just use sodium borohydride. Technically, just to stay consistent. Your book will discuss sodium cyanoborohydride, which is electronically tuned to be a little bit better for this, but to kind of keep things simple, you can use sodium cyanoborohydride. Sodium borohydride's fine as well. But the idea here is that you're going to condense, right? Now you've got the imine, right? That's not going to react with another equivalent of aldehyde, right? Because then you've got this tertiary, doubly, whatever amine, or maybe you could, but you know, that's not going to be as energetically favorable. You can at least do this reaction, right? And then when you treat it to the sodium borohydride reduction, right, you're doing the same thing that you would have been doing with an aldehyde. Okay, does that make sense? Yeah. I was just saying some acid source along with the aldehyde. Okay. So you take this molecule, you treat it with an aldehyde and acid, you generate the imine, which you all know. And so the only thing new here, which isn't really new, is that you can take the imine, treat it with sodium borohydride, it does the exact same thing that an aldehyde would do. Okay? There's nothing new here. But it's useful. I think this is a better time to teach it because we just learned about sodium borohydride and we just learned about imine condensation. So this is the time to learn this. So keep this in mind as well as an alternative useful strategy. Okay, so we've got about 10 minutes left. I'm going to start. I think we're making good time. So I think what I'm going to do is next class we're supposed to be talking about esters. I'm going to talk a little bit about esters today, and hopefully that'll open us time. If we can get through material on Wednesday, we'll have some time to, I think, do a little bit of refreshing, maybe do some synthesis problems or something to sort of get us moving forward. Because I think we're being pretty much close to done with carbonyls. Okay, so let's talk about reactions of esters. Okay, and esters and carboxylic acids, what we're going to see here is all the chemistry that's involved in these is going to be analogous to chemistry we saw before, tied in with carbonyl chemistry. Okay, but we just have to sort of understand some certain things. For example, we discussed a few classes ago the differences in reactivity, right? So if you take an aldehyde, or if you take a ketone, right, and you treat it with sodium borohydride, right, you're going to get the alcohol, you're going to get the alcohol, right? And if you had to guess which one of these, was going to be more reactive, which one would you expect would be faster of those two? Not a trick question.
Ketone.
Nope. Aldehyde, both sterics and electronically. Sterics is just more open because it's a proton versus the other thing. The other aspect is that the carbonyl is more stable. A ketone is more stable than an aldehyde because that positive charge character is a little bit more stabilized. But it turns out that if you move to, so this is a ketone, just let's refresh on terms. This is an aldehyde, right? If we move to an ester, the ketone is more stable than the aldehyde because of that sort of hyperconjugative stabilization effect, right? It's even more so in the case of an ester, yeah. Okay, it's even more so in the case of an ester, right? Now, because instead of hyperconjugation, now we've got full-blown conjugation, right? Now we've got a resonance form that we can invoke that even helps further stabilize the carbonyl. So it turns out that esters are extremely sluggish to react with sodium borohydride. Okay, you really, really, really have to push sodium borohydride with an ester, and sometimes it doesn't even work. And so, on the one hand, there's a nice selectivity that you can get, but for the sake of this class, I would say, sodium borohydride isn't going to work with that. You need something stronger. And so the stronger reagent that we use is lithium aluminum hydride. Okay, so it's basically lithium aluminum hydride. If you're trying to remember which one is more stable than the other, we can rationalize maybe by why a borohydride would be more stable than aluminum hydride. Right? Where's aluminum relative to boron?
Aluminum in the transition.
There's a periodic table right up there.
Aluminum's under it.
It's directly under it. Yeah, so right underneath boron is aluminum. Okay? And because of that, the aluminum boron strong is a lot weaker. And because of that, it's subsequently more reactive. So lithium aluminum hydride is much, much, much more reactive than sodium borohydride. In fact, to illustrate that, right, sodium borohydride you can oftentimes run sodium borohydride reactions in methanol as a solvent. If you try to do the same thing with lithium aluminum hydride, you'll cause a fire. You'll have a fire. Okay? Don't do it. Okay? But the other thing about lithium aluminum hydride, right, is, and specifically with esters, based upon what I said, is if you added the reagent to that, right? If we think about the mechanism here, what's going to happen, right, is as we go back to that sort of mechanism where we think about the hydride adding in. Right? That intermediate that I just showed right there, you can kick out an ethoxide, right, and regenerate the carbonyl. Remember how we kept saying carbonyl is a stable feature that we keep coming back to if something can form a carbonyl, it likes to form the carbonyl. So mechanistically, this can break down fairly readily and get to that aldehyde. Okay? But that aldehyde, as we just stated earlier, is highly reactive, right? The aldehyde is even more reactive. It's more reactive than a ketone, which is more reactive than an ester. So what's going to happen? It's going to do it again, right? So, not observed, right? So it's going to keep going. And what you're going to end up with is primary alcohol. So if you take an ester, okay, and you reduce it, it's not going to, first of all, important things about esters, they're generally not going to react with sodium borohydride, okay? Which means you have to go to a much stronger reducing agent, lithium aluminum hydride, okay? And the other thing to keep in mind about esters is that at least with lithium aluminum hydride, it's going to be very difficult to control reduction. Like, there's no way, I should say, not even difficult. It's going to be impossible to get it to stop at the aldehyde, right? Because the aldehyde is more reactive. Okay. All right, we're about out of time. I'm just going to leave you with one more sort of point, and we'll sort of lead off with this next week. There is a way that we can do this.
Wait.
I'm just erasing this. There it is. If we want to get to, we can get to the aldehyde, okay? We can get to the aldehyde, but if we're going to go to the aldehyde, we have to use something called diol. Sometimes it's diol H. What diol is a diisobutyl. Hope I got it right. Did I have the right isobutyl? Forget if the methyl's here. So forgive me. Somebody want to look it up? I think it's this. The methyl group's either there or there. So it's an isobutyl. Usually I just put R and then I started to get fancy there. It's an isobutyl. So it's diisobutyl aluminum hydride, and I forget which isomer of the butyl group it would be. Is that even a butyl? 1, 2, 3, 4. God. I don't even have a butyl. So then it's probably this. Pretty sure it's this. Whatever. The point.
We don't have to draw it, right?
Let's just go to this. All right. R. It's a trialkyl aluminum hydride, and I'm embarrassed that I can't remember what the isobutyl is. But the point is that it's actually diisobutyl.
It looks like
I just did tri, so I couldn't even do diisobutyl. Clearly, we're getting towards the end of the class. Why don't I save this till my brain is a little bit more fresh? But we're going to start off with diol the beginning of next class, and this is a reagent that can get to the aldehyde, so that's where we'll start off next class. Takes an ester to an aldehyde. Yeah, did I misspeak again? Yeah, it's best. Okay.